All right, let's go to rectified flows. Okay. Um, so today so we are switching topics. We have finished at least one theory arc. We'll come back to some more theory, but nothing as heavy as, I think for the rest of the semester, nothing is going to be as heavy as what we did so far, to be honest. Okay. Um, I want to switch to flow models. So many of you might have heard this term rectified flows. Um, and these are sort of the generative models at scale today. For example, flux, especially for images, this is the model at scale. So what exactly is this is what I want to talk about today. I'm going to take a certain narrow view of rectified flows. You could rectified flows start from optimal. So first I'll tell you what roughly it is, and then I'll tell you the viewpoint I'm going to take. Okay. Everything that I'm discussing today are from these following papers. The rectified flow was sort of developed roughly in parallel by three different groups. Liu et al., Chang from UT, that's flowing fast, straight and fast paper. Lipman's group, flow matching for generative modeling, and Albergo and Van den Eyden, which is normalizing flows using stochastic interpolants. Okay, these are sort of the parent papers for all of rectified flows. I'm also going to lean heavily on this paper by Raut et al., which was at iClear this year, okay, to talk about sort of the interpretation I'm going to take in this class. Okay, first let's talk about what the problem is and what the rectified flow view is. But I'm not going to go too deep into the transport theory. Okay. So when we talked about generation, we talked about it as, to a large extent in this class, we have talked about it as a sampling problem. Okay, you want to sample from some distribution P star, and this model starts from diffusion models or whatever, starts some noise, and then it incrementally denoises, quote unquote, to actually sample from the distribution of interest. There's another possible view for the same thing. We have also sort of thought about it, but we did, when we did DDIM especially, which is as transport. Okay, you got a sample of noise and find a transformation to map it to a point which is sampled from the distribution of interest. So there are two spaces. There's a space of noise, Gaussian or whatever else you want. Here I've just written Gaussian, but there's no reason it should be Gaussian. It's whatever you can easily generate, essentially. And so circular Gaussian is the easiest to generate. Okay. The other side is the data distribution. And you want to find a transport map to take couple between these points. That's another way. This is not really a sampling view. This is a transport view. Okay. And in these, so they connect. So now you can ask, what is the cheapest way or what's a good path and these kinds of things. What kind of path would you like? Quote unquote straight paths would be something you like. The reason is that if the path is straight, then it's easy to interpolate. It's easy to discretize. You don't need to interpolate when you're doing discrete interpolation of these continuous trajectories. You need far fewer number of steps to go from one end to the other. In particular, if it's exactly a straight line path, quote unquote, you can go from one end to the other in one step. Yeah, Constantine.
I came in late. So DDIM is this.
Good. I haven't even brought that connection yet. So basically what I said is that there are these over the last few years, people have started talking about rectified flow, and the parent papers are these top three papers, Liu et al., Lipmans, and Albergo and Aiden. And I'm just talking about that viewpoint which comes from optimal transport. Okay, and so this is not really a sampling view. This is a transport view. Okay, and now you can say that, well, therefore to generate a sample, if you find a vector field which is quote unquote straighter, or even continuous time, whatever it is, you can take the vector field and put as this input, this initial point, run that vector field to end up at the terminal point. And time is normalized between 0 and 1, whatever. Okay? One endpoint is 0, you move to time 1. We have indeed seen this kind of a thing in a different context, which is DDIM. This is what I'm getting to. So let's just step back and recap where we were then. Okay. What we did when we studied DDIM is the following. Okay, the stochastic view is very clear. You had a stochastic differential equation. It's an OU process that started from images and got to noise, used Anderson reversal, and then went back from noise to actually the image distribution, and that involved a different drift field which had the annealed score, and the diffusion field which is just √2. Okay, that's what we did with DDPM. I'm just doing continuous time. I'm back to continuous time. I'm not worrying about the discrete time at all for just now. Okay. And importantly, we also did an ODE version of this. Okay, we went through the Fokker-Planck equation, and then we said, hey, instead of running a stochastic sampler, you can you can come up with an ODE which has the identical marginals to this. Okay, these are the generative flow models when we did it with diffusions. Okay, this was from the Song et al. Papers. And the point there was, we constructed a time-dependent vector field, V bar. Okay, there were two vector fields, the forward and the reverse vector field. The forward vector field went from images to noise. The reverse vector field went from noise back to images. Okay, so yeah, and these vector fields were constructed using the Fokker-Planck equation. We went through the Fokker-Planck equation, matched the density evolution of the stochastic thing, and figured out what the vector field should be. We went through this whole business, if you remember, like several lectures back. Okay, and the upshot of all this was that the forward vector field was this following. It had this score in this, which is not surprising, okay, because that's how sort of the forward vector field had a score in it, and the reversal of the vector field was just invert the direction. So change t to 1 minus t if the time interval was 0 to t, and change the direction of the vector field itself because you're going the other direction. Okay, and this is basically the whatever we did with diffusions in the continuous time. This was an ODE interpretation. And then we said, hey, this has a flow interpretation, because now for this, if you initialize with a random sample of noise, then at time equal to 1, after this, if you run this deterministic differential equation in continuous time, what you're going to end up is a sample which is from the data distribution of interest. And this was not from we didn't try to optimize any costs or any such thing. Okay, that was not the objective here. We just came up with this differential equation which matched marginals of the stochastic differential equation. There is no optimal transport perspective in any of this. But nevertheless, you see, it is implicitly minimizing some cost, right? Because you could think of it as this differential equation is starting from some point of noise. It's a vector field which will transport it to a data distribution. And therefore, it is presumably solving some transport problem. Okay. So we have seen these kinds of samplers, and let's keep this in mind. So let's go back to rectified flows. So rectified flows start from the other side. It says that I don't want to start with a stochastic sampler and convert it to a deterministic sampler, which is what we did previously, but straight away let's think about a flow problem. Okay. And what you want is now you can start asking about this particular trajectory. Now I can say that, hey, I want to now design this trajectory so that it's quote unquote straighter, the path, so that when I discretize this thing, it's going to be easier to interpolate. Meaning the following. Okay, so if that statement is not clear, suppose this was the path. Okay, to get here. Okay, something like this. Okay. With this path, if I now do a coarse discretization, okay, and then take this would be my path, something. Okay, it is going to go crazily off. Okay, if the path is actually jagged. If it's smooth, then any straight line interpolation of 2 points, if it's not just smooth, if it's straight line, any linear interpolation by definition would match the actual path itself. So the straighter the path is, the more coarsely you can discretize this when implementing. Okay, so this is really the motivation for having straighter paths. All right. So starting from this, you can think of this as a measure transportation problem, to go through optimal transport, derive a particular vector field. I am not going to do that. What I want to do instead, if you want to go down the rectified field theory and what the properties it has, how it's designed, I would ask you to look at any of those papers, and there are many other resources on the web at this point. What I want to do is to connect this to diffusion models. So my goal for today's class, or first half of today's class, is to just say, okay, we have seen that diffusion models start from a stochastic evolution, and we can get a flow, you can get an ODE out of it. Okay. Question, rectified flows, we'll tell you what this vector field is. We'll say what the objective is trying to solve, and therefore it gives an ODE. So what is the connection between this and diffusion models? That's the question I'd like to answer here. Okay. So there are many other parts of it which I'm not going to talk about. I just want to talk about this in context of diffusion models. Okay. So what is the ODE you want? You start initially from the P1, which is the noise distribution. You run the reverse process or the generative process. At time x1 is from P0. P0 is the data distribution. P1 is the noise distribution. Okay. So you want to find such a vector field. In the DDIM, this was the reverse field, this V bar. Okay. So this is an ODE. Just as in DDIM, this can be reversed. So you can look at the forward process here as some U of t, ut, which will take a y0 sample from the data distribution, y1 sample from the noise distribution, and creates a coupling between them. Okay, and the relation between u and v is simply the following: you change the sign of the vector field from ut becomes minus v, and the time flows backwards, so 2t becomes 1 minus t. That's all. So going between forward and backward processes are trivial here. That which was also the same case with DDIM. Any questions so far? Just the basic setting. Good.
VT is just VT. Could be DDIM VT. Just something.
Right now, I've just said at this point exactly. VT could be in this up to this point. You could say one example of this. This is not rectified flow, but one example could be VT is equal to what DDIM thing is, and UT is the reversal of that. And so far, I haven't said anything beyond that. What makes it rectified flow is what is the cost function that gives a particular VT. Okay, and I want to talk about that next and the connection to DDIM. So deriving the rectified flow vector field for generation. Okay, so now we are sort of diverging from DDIM. DDIM was trying to match the marginals of the stochastic evolution of the reversal of the Anderson reversal of the OU process. Instead, here you're doing the following. So let's say we had access to we had an access to a noise sample. We have an access to a sample from the data distribution x0 and x1. So I want to do a interpolation between these two. The simplest interpolation is a straight line interpolation. Okay, time goes from 0 to 1. At any time t xt, I will write xt as equal to 1 minus t x0 plus t times x1. Okay, it's just an interpolation between these two samples. Okay, it's a straight line between these two. Good so far? Which means dx by dt, I'm taking derivative with respect to time. So these are fixed. So this is 1, and derivative of this is minus 1. So it just says minus x0 plus x1. Okay? So this is a differential equation. The problem is this is not causal, right? Traveling along this requires you to know both endpoints. It's not enough to just know one endpoint. So what is an approximation we can do to make this causal? So instead, we can say the following. Okay. Since this is not causal, I'll try to find a vector field that on an average satisfies this. Average over samples and time. What do I mean by that? So this drift is x1 minus x0. Okay. So this is v of xt. Okay. That's what vt of xt. Okay. That's what we have, right? That's your vector field. dx by dt is vt of xt. So what I've circled in red part could be DDIM. Okay, because it's just a differential equation that takes apart, and this vector field in DDIM VT was what is this is going from images. This is the VT, so it is xt plus grad log pt of xt with a minus sign on the whole thing, something like that. That is what the DDIM vector field is. Okay, so I want to approximate this by some VT of xt. So let's do that. So we take x1 minus x0. We'll try to find a VT. So t here doesn't mean terminal time. It's a random variable which is uniform from 0 to 1. Okay, so let's be careful about the notation. There are 3 random variables here: x1, the terminal state; x0, the initial time; and a random time uniformly chosen between 0 and 1. Are you good so far? And then what do? We just, and xt at that random time is 1 minus t x0 plus t x1. That's what we want. Okay. We want to find a vector field, ideally such that vt of xt is nothing but x1 minus x0. Yeah. Here you're sampling a triplet x0, x1, and t independently of each other.
But when I thought like the point of flow was it's a deterministic manner.
Yes, you couple, but what coupling? It's when you're constructing it, pick a random x0, pick a random x1, and I make a coupling between them. Pick yet another random x0, pick a random x1, make a coupling. This is my flow map.
But you might end up for the same x0, you might couple with.
But it's an average. So once could be, you're sampling that once.
Yeah.
XT is not integral from 0 to t.
No. That's why I've written.
It's exactly.
Exactly. Okay, this is what I'm saying xt is. I'm going to stick it. It's not what is the output of the function itself. That's why I've written that to be very clear what is xt.
V of 0.
So I'm just giving you now an optimization problem. I'm giving you a problem to find a function vt.
Like V of 0 should point towards the mean of P1. And then somewhere in the middle, it's like pointing other way.
We'll worry about what it does in a second. I just want to set up, first this setting I want to make sure. You're right. This we'll get to that in just a second. But I want to make sure this setup is clear. Okay. So since I'm just going to try to find a vector field, which on an average tries to satisfy this. Okay. There are other ways to think about it from flow theory and transport, which I'm not doing here. So read those other papers to sort of think about it there. I'm doing the minimal stuff needed to connect this to diffusions. Okay.
And also it's x1 and x0 are always in the same space.
No,
I guess I could put it.
x1, they're d-dimensional here. Yeah, the way it's written, yeah. This is in the latent. So we could do this whole thing in the latent space of a VAE, okay, or something like that. Okay, so Vt of x, so the usual recipe when we have these kinds of things, let's parameterize Vt by some parameter theta. That's your network, whatever the architecture is. It has two inputs, t and x, okay? And theta is, theta is learned from data. Is that clear? Excuse me. Just turn on. Got it. So what does this get me? I've just rewritten the objective. Okay, minimize, find a function, minimize overall theta, sample a triplet x0, x1, t over the product distribution, and patch this. So this is rectified flow. The v theta we get out of this is a rectified flow. Okay, this is a very unsatisfactory answer, and this is not the way the papers there describe it. There's more properties and all that. But I'll stop at this point for this to show you what this is in terms of diffusion. This is so the rest of the discussion in connection with exact DDIM is from this paper by Raut et al. Yes. This is same Jacob's. This is what Jacob's question is. This is what we are doing. Okay, x1, x0, t is not terminal time; it's a random variable. Okay, at that random time, what do you want it? It should be the interpolation between x0 and x1. So I'll just stick this in. At least this problem is completely well defined at this point. Okay. Okay, so you train this objective, and now I want to see what does. Now we'll come back and address what exactly is this doing.
Yeah, if you solve that, you actually get a sampler. That happens.
It's a vector field that couples. It is true, right? At both endpoints, it will hopefully be. It'll. Be,
does it take x0 to x1, or because you're taking on average things?
Yeah, but as t tends to 0, at t equal to 0, Vt it should be. Look at that. Look at what happens when t equal to t is close to 1. Yeah, when t is 1, this part is 0. This is just x1. So we will indeed at that close to that point, it will get it to x1. It is indeed a coupling.
Minimize this.
Yeah.
for-
Yeah, and the theta is well enough parameterized and all that stuff. You will indeed, with infinite number of samples, presumably it is coupling between these 2 points. What exactly this path is a rectified flow.
But
Hang on, I'll answer this, but I'm going to answer your question in a better way. Hold on for a few minutes. Okay, this answer is, I understand my answer is not fully satisfactory, but give me a few minutes. Okay, I'm going to derive what VT is explicitly. Okay, and this is what in the paper Raut et al. They actually wrote this out exactly what exactly this thing is. Okay, so if you just go to the Fokker-Planck and write out what this thing is, it turns out this is just a reweighted DDM. That's the point I want to make. Okay, so condition on capital T is little t, and xt is little xt. This is the function you have. Okay, it's nothing but we know that if you want to solve this, okay, for a fixed capital T and a fixed for a fixed capital T, this is an MMSE problem. Therefore, the optimal V theta should be the conditional expectation of x1 x1 minus x0 given this thing. Good. So that's all we've written here. Okay. So MMSE, the optimal solution is the conditional expectation. Okay. So let's say that we have solved it. This V theta is infinitely parameterized so that we have actually solved the MMSE problem. So this is all under the assumption theta is infinitely strong. Okay. That parameterization is rich enough so that you can actually solve everything right. Okay. So in that case, then this is the process that transports noise to data, whatever this conditional expectation is. Similarly, we can do the forward process. Ut will be the negative of v of 1 minus tx, okay, which will couple y0, y1 from p0 cross p1. Yt interpolates between y1 and y0, t times 1 minus t. I'm just writing the same thing the other way around. Okay, and so what you're going to get is a forward flow transporting data to noise will be ut of yt, which is y1 minus y0 given yt equal to t. So let's derive a closed form expression for this. The claim is that ut is nothing but this. It is minus yt by 1 minus t by 1 minus t grad log pt of yt. Look at this for a minute. This is very, very similar to the DDIM equation. What are the DDIM equation? This is the forward moving from data to noise. Let's go back to DDIM. This is the DDIM thing. Okay, negative of x plus grad log pt of x. Okay, let's keep copy. Go to 15. Paste. I'll just change the color for just now. Okay, temporarily this can be there. I'm not going to stick it. So let's look at these two equations. You see, it's essentially the same thing with the time scaling. X, I'm doing a 1 minus t, and the other is t by 1 minus t. The coefficients are different, but it's still an affine function of score. Okay. What does this mean? It basically means it's accelerating things differently. What does this coefficients of 1 by t, 1 by 1 minus t mean? It means as t is going to 1, this thing is blowing up. So it is essentially a time. So if you do a particular discretization of DDIM, okay, what this means is that you're doing a different discretization of it. It's taking maybe way more, it is rescaling time to take some parts of the state space for the discretized one of the trajectory and have far more samples there and far fewer in the other part, given an equal number of discretization samples. Okay, it's a time rescaled version of DDIM. Okay, that's basically what it is, and that makes sense about straightening as well. If I take any curve, increasing curve, I can make it like a straight line by two ways. Either I can make the function itself straight, or I can warp the x-axis differently. Right? If I want to say that, hey, the curve looks like this, I want to make it look straight, I will do a nonlinear warping of the x-axis. I can, whenever it's going fast, whenever this derivative is high, I can stretch it out. And whenever the derivative, so that's really what is going on. Okay, it is just a time, it's a rescale, and x-axis is time in some sense. So it's a time scaling of what is going on, which means I'll derive this in a second, which basically means if you have a RF and you want a DDIM, you can easily, you have a denoising box, which is an RF box, and you want to do DDIM with it, it's easy. Figure out what the difference in coefficients are and just reweight it. Okay, it's just a multi-weighting. So in fact, people have used it this way. I don't want to talk about which company, but internally for large-scale models which have been already trained to be DDIM, and they, for some reason, they need a flow model, you can just use this equation to go between that for if you need such a flow model. Why do you want one model versus the other? Because maybe there are downstream tasks which are being trained with one type of model. In which case, then you want a RF model, you want a DDIM model, you want maybe a stochastic model. I'll talk about that as well. You can use whatever model you want once you have one base model, because they're all finally different affine transformations of annealed score. Okay, that's really the point I want to get across here. What is the objective for what I have pushed under the rug is what is the what are the properties of this trajectory and all that. That's the RF. There's a lot of beautiful theory which I'm not going to talk about. Yes.
You just get this by looking at the reverse OU drift and changing time.
Yeah, I'm going to show you now. Good. I will answer your question in about 10 minutes. Okay. Okay, good. So now let's derive this. And in deriving this, I think implicitly you're going to answer your question. Okay. But I'll explicitly do so as well in a minute. Yeah. Okay. So why is this true? Remember this my claim. So what is the claim I'm having here? That this conditional expectation, when you define it with that straight line, sample path straight line, leads to the vector field, the averaged vector field, which looks like this. Okay. The proof is the following. Okay. So look at PD's formula. So suppose I have some random variable R0. I noise it with a Gaussian with variance sigma square, okay, times identity. Then I define RT as this. Then remember what we derived this from 3D's formula. We said the conditional expectation of R0 given RT is affine in RT. This was our key derivative. This is lecture 5-4 somewhere back there, right? It said that is RT plus sigma square grad log PT of RT. Okay. So now let's look at these two things. This is now we have yt is 1 minus t y0 plus t y1. So 1 minus t y0 is R0 here. Sigma is t. So let's just substitute. Therefore, expected value of 1 minus t y0 given yt equal to little yt is yt plus sigma is just t. So t square grad log pt of yt. Just copied that down. Okay. So now we can divide both sides by 1 minus t. It says that the conditional expectation of y0 given yt is little yt is yt by 1 minus t plus t square by 1 minus t grad log pt of yt. Simple? Okay. Now, also we know sample-wise, yt is 1 minus t y0 plus t y1. And therefore, y1, I can just rewrite, taking this to the other side, is yt by t minus 1 over 1 minus t by t y0. Okay. Therefore, I can take conditional expectations on both sides. Expected value of yt given y1 given yt is yt. This is yt, so it just pops out itself because that's under the conditioning. This is E of y0 given yt is little yt. Okay. And so substitute this. For this, we now have an expression here. So we just substitute that in. And so what do we get? We get yt by t, 1 minus t by t, and then this whole thing comes in here, which is what is written. Okay, so you can cancel this. You can cancel this. You can cancel this. Okay, which will give me that conditional expectation of y1 is minus t grad log pt of yt. So that means ut is y1 minus y0. You just put this together, and that's all there is to it. It's a very, very simple derivation. There's nothing fancy here. And therefore, the reverse field is all that stuff. Change t to 1 minus t, and yes.
A little bit like when we construct this vector field, how come we don't use knowledge of x0 Or of the noise that we draw.
We want a differential equation should depend only on the current state. It depends what you want. Yes, if I want a vector field, I'm just saying that why we are doing there are two questions. What are we doing? We are saying, suppose I'm an xt, I want to decide where to go next based on where I am right now.
Yeah.
Okay, which means that vt should just be a function of xt.
Like the X0 could still show.
It could, but
I guess we originally said like.
I agree. You could do all sorts of things. Okay, which is why I'm not doing. These things can be generalized way more. Look at the stochastic interpolance paper. That actually talks about going between sort of interpolants of various sorts. Their SD and OD connections. There's a lot in that paper, which will you could look at why should I do this versus something else. Yeah, you could. But all I'm trying, so this class is about, this is rectified flow. What is the ODE and SDE for that? That's all I want to explicitly. And the reason we are doing this is because RF is so important in practice. Okay, so I'm just working out essentially 1970s theory, okay, or 80s theory, nothing more than that. Because this is just Fokker-Planck equation and standard SDE stuff. There's nothing fancy I'm doing anywhere here. Okay? We're just working that out. That's all is going on here. Okay, now, so we have this as the flow equation. Now I want to understand the density evolution of this. So we did study the Fokker-Planck equation. Remember, it told you the density evolution of a stochastic differential equation. If I put sigma equal to 0 in an SDE, then I could look at the density evolution of essentially an ODE with a random initial condition. This can be derived independently. It's called the continuity equation. It's a special case of the Fokker-Planck when sigma, there is no diffusive field at all. Okay. And again, the intuition goes back. We did do the intuition for that before we did the Fokker-Planck. If you remember, I talked about mass, about transport, just conservation of mass and things like that. Okay. So this essentially leads to, if you do the continuity equation, then you'll get the density evolution as the divergence of whatever the vector field times pt. So, okay, so now we know what this density evolution is. Now we know that whenever we see a grad log pt times pt, we can make an SD out of it, right? You can always pull that back and forth. The whole log trick, the second order term when we did the Fokker-Planck could be pulled into the drift term or push it back into diffusion term.
That's how we got DDIM.
Yes, that's basically, the way we got DDIM is, we wrote the SDE, we had a del square p by del t square, del x square. We wrote it as del by del x of grad p, okay, which is nothing but del by del x of grad log p by p times p, and then you just pull this in. So this is the usual trick. This is a log trick for going between a second order thing, second derivative thing to a first derivative thing. Okay. So here is the so look at this particular SDE. So the OU process was, this was just √2, this was just -1. So now I'm getting to the question, answering your question. This is a different time change. This is a different diffusive field. Okay. Let's write the Fokker-Planck equation for this. And not surprisingly, it is this. Okay. So that's all there is to it. It is, so you can interpret a rectified flow as just a different you're not doing the reversal of the Anderson, you're doing something else. It is this.
So I do some calculations to show that OU took us to a Gaussian. Back when you first, at the steady state distribution of running.
Yes, we solved the density evolution.
It's like by design, or do we also have to prove it?
There is not, I mean, it's by design because x1 and x0 was coupling. Okay, it's coupling between x1 and x0. It is by design, but it's also true. We can check it by verifying, because I've written the density evolution there. Check what happens with this density evolution. There is a problem here which I'm brushing under the carpet. There's a 1 by 1 minus t, and these things don't satisfy the noise assumptions. These things blow up at the endpoints. Okay, by the time you hit the actual manifold of interest, it's not clear that this SD is even well defined. Okay, yeah, is which one?
In line 3, whose rotate is
PT?
PT.
Yeah, PT is the density of this value. So PT is the density of the following system. dxt by dt equal to ut of xt. With x0 is basically whatever the it is. Image to noise. This is the forward process. Yes, I'm doing everything in forward here. So I'm doing everything in the forward process here. I could have done everything with the reverse. I just chose to do everything with the forward process.
That, P,
So look at this density evolution and check what is the terminal. I've given you the density evolution at time equal to 0. What is the density? If I start with that, check that at time equal to 1, it is indeed a Gaussian. Because at time equal to, yes. The other way to look at it is, look at this. This is basically, okay, the OU process goes from time 0 to infinity. What this is doing is to accelerate time such that it goes from 0 to 1.
Yeah, but if I change times, like I'm gonna get an extra term. Like I can't just prove that this has the correct limits by changing.
At time equal to 1, what happens to this? This should be essentially a Gaussian. Gaussian zero mean unit identity.
Do you have any comment on how you do this?
Has that this density evolution? Okay. So I need to solve this differential equation, and to show that time equal to 1, it has that property. Let me just see whether I can immediately prove this by just looking at it.
It's like timely homogeneous though, right? It's not the problem basically. It's that the right hand side has like a time dependent generator, and that's the scenario in all of these cases.
The way the way I would do this, good. The way I think I would do it, I'm just thinking aloud now, is to do a time change. To map 0 to 1 to 0 to infinity, and then it'll give back the original equation. Will you get we'll just get, I think you'll get the same AU. Will you get, I don't know what you will get. Okay. So I'm not able to think real time on this, but okay. But there's time compression happening from 0 to 1, 0 to infinity. That's really what is happening, which is why that 1 by 1 minus t is going on in this business. Okay. But this is the SD. But there's another question. How do you actually implement? Okay, let me finish the story and then come to the implementation story. Give me just a second. Okay, so we can write the SD equivalent of this thing, which is this one. Okay, so therefore now it's saying one more interesting thing, or a useful thing, which is that if you have an RF, somebody has designed an RF for you, and you want a stochastic sampler, okay, then you can actually use the RF to get, you can actually get from the deterministic RF, you can actually get a stochastic sampler out of it. Now your question is, why do I ever want a stochastic sampler? Okay, maybe because I thought the whole point was to come up with a fast ODE-based solver. There are several reasons why you want a stochastic sampler in practice. Sometimes. One, there are a lot of tools that have been built, downstream tools, which use a stochastic for DDPM and a stochastic box, which requires the stochastics in it. So if you have as models are scaled up, you've got better and better models, but which work with flows. But can I use the old tools with a stochastic pipeline? And the answer is yes, because now we know what is an RF's SDE equivalent. Okay, that's one point. The second is that a stochastic sampler has some advantages over a deterministic one. The following: if you're following a flow model, okay, deterministic flow, you start from a noise sample. Of course, it's designed so that at the end of whatever the time horizon, it's going to give a sample from the data distribution. But suppose you discretize it, or there is some error, or some quantization error, or something. Errors are deterministic systems are going to have error propagation. The Gronwall's inequality will say that over time it's going to, in the worst case, exponentially deviate from what you want it to be. Okay, so stochastic samplers are attractors. So, for example, if you run an OU process, okay, it's always attracting back towards the Gaussian distribution. So something happens wrong at some point, it'll go back to the Gaussian anyway. Okay, so there's a sort of stability of stochastic samplers which are useful. So if you're willing to pay the connection, if you're willing to pay the price to actually run a stochastic sampler, it's been observed that at high sampling levels, stochastic samplers have generate quote unquote better quality results than indeed deterministic samplers. Okay, so therefore, in some applications, you may want a stochastic sampler. In which case, this tells you that it doesn't matter which way you have trained this model. You can rescale. The coefficients matter in terms of other properties, but given that you want to come up with one type of model, it's very easy to move between one to the other by just without retraining anything, by just changing the parameters in your sort of inference code. Okay, that's really what the point is here.
So then which should I run and what should I learn? Like I recall we were trying to learn like VT, which is right now.
It doesn't matter. You learn any one VT either using DDPM or using rectified flow or whatever else you have. All of this finally gives an affine transformation of score, of anneal score.
Learning deep data
from this triplet. You sample these three things. This is called conditional score matching. The word in the literature for this is called conditional score matching.
Yeah.
Okay.
I can also just do what we did before.
run this SDE, right? Yeah.
And learn.
You could.
What is the
that
perspective?
it came from the all I'm saying is do whatever you want. If you run conditional score matching, you will get a denoiser which has this interpretation. If you run DDPM, you will get a denoiser which gives a different weight. Which is better in practice is a separate story. But do whatever is essentially decoupling two things. One is learning the score versus how do you use it for inference. Okay, now it's clear that you can mix and match in whichever way you want between these things. That's really the point. I'm not trying to I'm not trying to claim that one is better than the other or any such thing. I'm just saying that it's just different weights and it's clear what those weights. Now you can start arguing about what's the right weights to use and whether it's straighter and all that. That's a separate story.
But just in terms of learning the score, we now have two different squared laws.
They're just two. There are other ways as well, all of which find essentially there's something called slice score matching. There is something else.
One dominant.
There are over time, I don't know which is dominant today. Something was dominant last week. Something will be dominant tomorrow morning. Okay. Sorry.
I have a plus qualification and I use this to write something. Is the qualification?
People have. I can show you image. I can show you images on that's the DieClear paper. You can see what the quality of these things are. And there are also other papers which are done stochastic sampling using that. So I would say you start from this paper and you can actually see images and so on. I didn't pull it in here. They wrote that all paper. You can do all and people have used it for other applications. So, okay, from this paper, yeah.
So the ODE which you get finally for the rectified flow is almost exactly the same as the DDI ODE, just with some few time scale.
Of course.
So if you ran DDI with the correct choices of
yes,
alpha T and beta T, would you recover exactly the same thing?
With the up to discretization without blowing up?
With discretization. With the correct
yes. Which is what I sort of alluded to. I said there's a big company which has a really good DDM model and they needed RF and they're just doing, if you change the alpha T beta, it is literally a code change on the weights to get from one to the other. Okay. Yes.
But this you have applications for your like ODE solver because as you approach one, that's going to happen.
Yes. So in practice, what you need to do is to stop because these are the image world. The images are really nice in the sense that the human eye produces the last step of sort of smoothing things out. Okay, you never go to t equal to 1. Go to t equal to 0.95 or something and 0.05 and stop. And then take that as slightly noisy versions and things are okay. Okay. That's practice here. Okay, so that's all I wanted to say about RF today. Okay. Of course, there's far more about rectified flows. I haven't for example, what I did not talk about is if you indeed solve that problem, what are the theoretical properties you get? And I would suggest look at these three papers also there are blog posts online for checking any of these kinds of things. The first three papers are really nice and you should look at that. Also, there's something called reflow. You can take a flow model and then straighten it further. Again, I'm not talking about any of those kinds of things. But So reflow requires a RF for a flow model, which you can flow again. But now you realize that you could do the first stage of reflow with a DDIM model. If I already have a DDIM model, then I can take that and start from that and reflow on top of it, because essentially it's also a flow model. You can do all these kinds of things, but that's going down a rabbit hole which I don't want to in this class, because this is about diffusions. And so I will stop with this discussion here, and I want to move on to the next topic. Okay. We are doing a major change in direction now, which is posterior sampling. Okay. So far, the problem is the following. I have an unknown, I have a distribution P star, and I want to generate samples from P star. We talked about how to train such a model for P star from samples, or if you have a normalized version of. So there are multiple issues with it. One is, even if I'm giving you P star, how do I draw a sample from it? That was something we talked about. And the other was that if I give you just samples, can I draw a fresh sample from it, whether you explicitly learn P star or not? Okay, this was the other thing we talked about. But we are going to change but finally, why do you ever want to generate, especially in the generative model setting? If somebody says generate an image, that's not a very useful thing. Or in text models, generate a paragraph of text. Okay, these are not very interesting things to do. I mean, it may be fun, but it's pointless, right? What you really care about are one of few things: contextual. I give you in text. Let's start with text. I give you a question and generate an answer to this question. If it's an image, I give you a blurry image and say clean it up and give me a clean image. Or I give you a text description, generate an image of Sanjay standing in front of a classroom, and it should generate. So it's always contextual. I give you some context, whether it's image or text or whatever, and you want to generate something consistent with it. Mathematically, you can think of this always as generate. So I have a model Q star, or P star, which is over the object data of interest. Can you sample instead from P star of dot given Y, where Y is whatever your context is? This is where sort of metal meets the road in some sense. The generative model is super important, but I want it because I want to solve questions of this type. Okay, and this is called posterior sampling. So now I'm going to switch to posterior sampling. Okay. So this lecture note is long, and I have drawn from various things, including Advait here and Litu, who helped me a lot with the stuff, with these notes, and a bunch of papers. And I will start talking about these papers. Let us see. There are about 15 papers in this set of notes. I'll bring up these papers as and when I talk about various methods. Okay, but before I want to get to any of these methods, I want to just start with sampling and optimization. Okay, so to start with, maybe the only reference I want to highlight at this point, I'll reference the other ones, is Andre Vibisano's paper on sampling as optimization from Code 2018. Okay, it's a really, really nice paper to look at. Okay, so first, let's look at the posterior sampling problem. So now, the only time in this class, maybe still now, I've never shown you an image, despite the fact that it's a sampling class. So let's talk about the kinds of problems we want to solve. So we have a generative model, P star. So there's a black box that can sample from P star, whether it's a DDPM, whether it's an RF, whether it's something else, whether it's maybe even Monte Carlo, whatever, Metropolis Hastings, you've got a P star. But now I'm asking you to sample from P star of X given Y, where Y is some side information or measurement. For example, if you're looking at image problems, things like this. I've given you sort of an input which looks like this, which is a blurry image, and you want to sort of clean it up. Or in terms of, so this is the cleaning up, okay? Or this could be Gaussian deblur, which means that you got this and you want to get that, so on. Yes. But that's not the point of this thing. I just want to give this an example. It's just easiest to copy and paste from my own paper and from paper. Yeah. Okay. So this image is from this paper, Raut et al. In CAPR 2024. And or you can do, but you can do other things as well. What Y means. Y basically could be an editing. It does not need to be in the same space as well, right? Y is just in terms of an abstract problem. I want to sample from P star of X given Y. Y could be whatever your side information, and as long as you have some way to sort of build a joint distribution X and Y, you can, or you have a way to sort of do sample from conditional distributions, you're in business. The Y could be change a cat to a cat wearing glasses. Okay, so
You have to noise the original image. Is this the one where you re-noise it and go back?
the algorithm is whatever, right? You're talking about algorithms for how you do this.
If you condition that left image on middle truck, I mean, it's inconsistent.
No, that's why it should be consistent with the. It's not just yellow truck. The caption needs to be, here is a noisy image of a white truck. Convert this to a yellow truck using the input of this daughter. You know, it's some paragraph of blah. Yeah, I describe something. It's not clear. You need Y to be descriptive enough to make sure that you satisfy whatever your constraints are. And then you want to sample from P star of dot. Yeah. Whatever you want, and it may not Y may not be even a scale, a text string. It could be Y could be written as Y1 colon Y2, Y1 comma Y2. So Y1 is, for example, this image, and Y2 could be a text descriptor, and you want to condition on Y1 comma Y2, and presumably Y1 and Y2 are consistent with each other. Otherwise, you see, the measure is not meaningful. So all those things mathematically, when you start thinking about it, you need to do all that. But I'm assuming that whatever your conditioning is consistent, and then you want a conditional sampler. That's all. All I'm trying to motivate is posterior sampling is actually a useful problem. Okay. You can do stylization with it too, but we will see some of these images later, so I'm not going to get into it. You understand what the story is. Okay. So let's get to so done. I'm not going to show you any more images. Now let's get back to business. Okay. Back to business is the following, that I want to solve posterior sampling problems. So let's start just thinking about, so this is, you want to look at Vibissono's paper. That's what CF7 here is. But here is the problem. Okay. You could say, forget about sampling. I give you Y, I give you a loss function, and find an X that minimizes this loss. There's no sample, no anything. Example, okay? So there's a X, there's a measurement operator A, there's some additive noise to this, and you want to sort of, you want to construct a Y such that minimize the L2 error between, you are given this Y, which is your measurements. You want to solve the inverse problem to figure out what this X is, which is through this measurement operator. Meaning, right? So Y is a given single item here in this case. It's not a random variable. Don't think about it as a random variable. Y is given. Okay? And then I don't know X, but I do know A. Okay. For example, A could be a model of a camera system or something like that. Okay? In which case, I want to find an X that is consistent with Y. And if there's a unique solution to this, we know what to do. And if A is, for example, A is just a matrix, and there's a unique solution to this, we know how to solve this. Just solve this, it's a linear, you need to solve, you can just find this using whatever, just linear algebra essentially. Okay? But if this problem is ill-posed, meaning maybe there are many X's consistent with this Y. And now let's look at this problem. This is typically the kinds of inverse problems you care about. I give you a pixelated image. If I think of an image as just a very high dimensional vector, okay? So a 1024 by 1024 image is 3 million dimensional vector, okay, roughly, because it's 1024 times 1024 times 3 colors, RGB. It's of that order dimension, okay? And I give you a pixelated version of it, okay? I wipe out like 50% of the pixels and say, fill it in. There are infinitely possible things that are consistent in the ambient space. So, right, there is no unique correct solution. Okay. So one thing you could say is, even though there's no unique solution, I'm going to regularize it so that I bias it towards some kind of solution. Okay, you have seen all sorts of regularizations for optimization problems, 2-norm, whatever. So what the kind of regularization I want to think about here is regularization through a generative prior. What that means, we'll talk about it in a second. Okay. So, but in general, you could say this is my loss function. I'm going to add some regularizer. What does that mean? That means that essentially I just make this a convex problem. Well, that's not quite correct, but effectively, I'll make this nice enough so that this will have a unique solution. If I put some G nice enough, and then I'm in business. But there's another way to, so this is optimization perspective, which I'm done with now, and which you can spend 2 semesters with Constantine here thinking about this. So let's think about a sampling way of thinking about exactly this problem. Okay, so the problem, I haven't changed the problem yet. I've given you a y, I want to find an x, okay, which solves this inverse problem. One way is to reformulate this as the following. Hey, let me, instead of finding an x, find a distribution q star. Okay, I'm now asking you to find a distribution q star, which is the following. Q star solves this following distribution valued optimization problem. Let's look at this. It says there is some ground truth distribution P star, and I want the Q to be close to that. So I'm going to put a KL regularizer on that. Okay, the divergence. So this is trying to make Q close to this P star. And furthermore, yes, it's a reverse KL. It's important in the, you can't, okay? You can't. I want a Q such that when sampled from Q, it's close to P star. Yes, okay? It's critical there's a reverse KL, and we'll see why it is so. But now, this is my loss function. So under this Q, suppose I could sample, this Q is a distribution, I'm going to sample an X, and I feed it to that loss function, okay? Then I should get small loss. So whatever samples I generate should be consistent with my measurement, okay? So in the special case where there is a unique solution, okay, in this case, and I put the weight of this to be really small, you see that this Q could be just if this was not there, there's no regularizer here. And then the optimal solution, in case there was a unique solution to this, would be Q would just be a delta function on the true value of X, okay, in this case. But in general, it's going to be some distribution. So this is what I mean by regularizing through a generative prior. So it's a sampling-based way. This is the prior, and it's a generative prior because presumably I have a generative model. P star, I don't actually maybe have access to P star, but I have a box which can sample from P star. And I want to instead sample from Q star. Okay.
The same as, right? I mean, it's the same idea.
As?
Like before G, like.
It is exactly the same. All I've said is that instead of solving an optimization problem to find an X, I'm going to formulate an optimization problem as finding a distribution and then sample from that distribution. That's all I'm saying. In terms of the pipeline, it is different. The first pipeline returned a sample. This pipeline, it returned an X. It returned a deterministic X. There was no random. It wasn't a sample. It was returning a solution. This pipeline is returning an X. This pipeline is returning a Q star, which then I need to sample from to actually get an X. And every time I do this again and again, I'm going to get a different X. Okay. Why do you want a sampling perspective as opposed to an optimization perspective in some of these things? So this again goes back to a bunch of papers. For example, Alex DeMarcus has worked on it, but many other people before that have worked on this problem. And hang on.
The inside of the expectation, the optimization part, just the inside.
I'm talking about something else, which I'm confused. I'm talking about maybe I'm answering a question you did not ask. That's what I'm wondering. What is your, maybe can you repeat your question once more?
Plot star, then you're just saying minimize the
Jeez.
expectation of that under samples from Q.
But the space here is different. Do you see? This is an optimization over an X space.
Yeah.
This is an optimization over a measure space. So that's what I'm saying. So these are not the same problems.
at the end of this loss function, you find a distribution.
Exactly. Exactly. The way I've written it here, at least, I may or may not do this, but the way at least so far it's written is, we have written an optimization problem over distributions. All this is going to return as a distribution. And to actually get a sample, now I need to sample from this distribution. And every time I sample, I'm going to get a different solution. Whereas in the first pipeline, every time I resolve it, I'm going to get the same X. I'm not going to get a different X. So it is a different, conceptually, it's a different pipeline in that sense. So is that what you are trying to get at? I'm not sure.
I guess the top one is like the MLE, and this is.
Exactly.
It's the same idea.
It is, but now the question is the following. So MLE can be sometimes very bad. In images especially, it's going to, suppose that the manifold you're sampling over, what does MLE do? If squared loss, okay? If it's a curved manifold and you've got a noisy image, okay? You're going to average over all possible images consistent with it, right? With the correct conditional distribution. That's what it's doing, the conditional expectation. But this point is going to go off the manifold. The average of a collection of points lies on that space only if that space is linear. Okay, so a better. Do you see what I'm saying? The condition, depending on the loss function, I'm just giving you the condition. Suppose I put a squared loss. Okay. Yeah, I'm putting a square. I've said that the density of interest is a curved space. Okay. Then you're taking some conditional expectation over all on some, and you're given some information. What you're going to get is a conditional expectation with respect to some tilted measure distribution over that manifold. And that average in general will not lie on that point is not going to lie on the manifold itself. So if I take a curved space and put some density on it, the average of it is not going to be on that curve. Think of a two-dimensional space with a circle, okay? Let's say that all the data distribution lies only on this circle, okay? And I give you the,
Yeah, why maybe it's taking us far afield, but like, why would we average if we're just taking MLE?
so if I'm at this point, okay, and the optimal solution is of this form.
Why is it?
Because for a squared loss, the conditional expectation is the right thing to do. It depends on your loss function. If my loss function is a squared loss function.
I guess like what Jacob said, I agree with. Like every point, I'm going to have a loss plus a term that comes from a likelihood. The likelihood's going to be infinite, plus or minus infinity, when you're
Okay.
trying anywhere off. So you're just going to get one best point whatever that is, and it's going to be on the manifold. You could solve that problem. Maybe you can't solve it.
It depends what, okay, it depends what the optimization problem you're solving is. If you're simply solving the following, if I want to just solve a problem that minimizes the L2 loss, that's what I'm thinking of. Okay, I want to minimize, say, y minus ax whole square.
Yeah.
That's all I want to solve. Okay, then
Plus log line.
no, I'm not doing any regularization. Okay, then what would I get? That's all. That's what I was thinking. So I was thinking about just that. Yes, if you, in general, this is the issue with optimization-based solutions. Without the right regularizer, it's not even clear that the solution is going to lie on the manifold of interest. That's all I'm trying to say. Okay.
Actually, some manifold within R.
Yes. Images are okay. So maybe I should.
Coarsely, but I can't actually know the image.
Exactly. Precisely. So what? Okay, good. Let's restate this discussion. So suppose that images lie in a 12,000 dimensional manifold in a 3 million dimensional ambient space. Okay, it's presumably a curved manifold there. Okay, and I don't exactly know how to regularize. Suppose I just solve the unregularized problem of least squares, then the conditional expectation will lie off the manifold.
So you're in the ambient space.
Yes, you're not on the manifold space. You're in the ambient space. So in this case, suppose you have a sampler from that manifold instead and solve this problem, you will then return a valid image. Okay.
Have the prior.
Exactly. Do you see the reason why we are going down this road?
Yeah.
Okay. So this is the.
Otherwise, you take the GAN approach, which just says you have to be on the manifold. Like I could just, but this is it's about the access we have to the distribution.
Yes, it's about,
Can't compute a log line.
yeah.
I can just say.
That's right. So I didn't want to go down this whole, all I was trying to say is that just solving an unregularized optimization problem could lead you off the manifold. That's all I wanted to say. If you have a generative prior, you can make sure that whatever you return is on the manifold. That's really there are maybe other ways to do that too, but I'm just saying that's sort of one motivation for building a sampler. Okay. All right. So look at this sampling problem, okay, which is what we want to solve. And I'll just finish up this one derivation and we'll close up today. Okay. So this part is to sample from Q that minimize the expected loss, and this is close to this P star. So we can write that Ly of x as negative log of e to the minus Ly of x. We can just rewrite it this way. Okay. And KL is Q by P, the expectation always with respect to Q. And here too. So this is the optimization problem. So we can rewrite this by taking this negative log e to the minus L and move it to the denominator. So it's nothing but Q by P star e to the minus L. Okay. And so what is this? This is this. So let's write this. Let's write Z. This is not a random variable, it's just this normalizing. I'm just going to write this integral as Z. Then this can be rewritten as log Q. I'm going to write 1 by Z here and the minus log Z outside. Okay. Right. So look at this. This is nothing but the KL. This is Q, Q, and something. This is a valid distribution now because we have divide by Z. That's the normalizing constant, which means this part is just the KL divergence between Q and this whole thing. Okay. And there's a minus log Z. So this one doesn't have any Q at all in it because the Z is just P star e to the minus L. So I don't need to worry about that when solving this optimization problem. So what is the one that minimizes the KL? The Q must be equal to this. That's what gives you the zero loss, which means Q star is P star e to the minus L by Z. So essentially, this is what we mean by we want to all sample solving inverse problems when you're regularized by a generator model is equivalent to sampling from a tilted distribution. You might have heard this statement thrown around sometimes. Now, this is exactly the proof of that. Okay. If indeed you want to solve this inverse problem with a KL regularizer with respect to a generative prior, then it's equivalent to sampling from P, which is exponentially tilted with respect to the loss function. Okay. So, and this is, yeah, question?
This setting, you're saying we don't necessarily have the exact form of P star of it, but we have something that can happen.
We'll worry about, now we are going down to zoo of algorithms. Suppose you have exact P star, then I need to do this. Suppose I don't, so we need to now start talking about algorithms. But before I went to any algorithms, I wanted to motivate where posterior sampling and tilted distributions are coming from. So what is the posterior sampling view of it? P of x given y can be, so how do we write this? We need to write this as is proportional to P of x times P of y given x. And P of y given x is e to the minus L. So conditional distribute, if I want to sample from P of x given y, that again is a question of this form. It's P star with that exponential tilt, where the tilt is whatever the conditional of y given x. And note that in the measurement setting, what is if you have Gaussian noise, P of y given x is exactly equal to e to the minus y minus ax whole square by 2, okay, which is L of x. So you can see the connections between sort of posterior sampling, tilted distribution, and generative prior regularized optimization. Okay, they're all very closely connected, and so we will use these things interchangeably. Yes.
If I don't have access right now, for example, so if I did have access to like the gradient of ProStar, I could say to you like, oh, you're going to run the Lanchon algorithm and tell me what goes wrong. If you don't have access to Grad ProStar, do we return to the previous thing, basically?
It's good. This is several classes of what can be done. First, if I have access to the score of P, I don't have access to P star. Typically, I have access to grad log PT. Okay, the annealed version. Does it mean that I can easily do this? The answer is no. Okay.
Yeah, just do fun.
This actually is, so in fact, even if P star has a LSI, Q star may not. Okay.
Yeah.
Okay, and vice versa. So there are lots and lots of issues, but that's what I just wanted to set up this today. I just wanted to talk about the pipeline before we go into all these kinds of technical issues.
We don't have in mind that P star is like a log concave that exists.
P star is the canonical example is P star is the density of is the distribution over a manifold of images, and I want to do image stylization, blah, whatever else I want to do. Okay, that's the running example we have in mind. Okay, and so next class onwards we will start going down the road of posterior samplings that are correct in theory but don't work, and posterior sampling that are wrong in theory but work. Okay, both of those is what the next few classes are about. Okay. Then this breaks down. But there is. It's not. It's no longer a tilted distribution. It's something completely different. I don't know. I don't know what even that is. Right. Yeah. Log expectation.
No, but in terms of the mode.
Ah. If you are in an underparameterized setting, and this is how the ground truth P star looks like, the forward KL will average across all modes. The forward KL will return a Q star that looks like this.
The forward KL is
P star Q.
okay.
Okay. The reverse KL will go this way. That is Q P star. Okay. That's sort of what in an underparameter. But if it's over parameterized, none of these. Yeah.
The first argument is I only care about samples that come from the first.
Yeah.
So if I don't care about P star, I can just take its base.
Okay. Let's stop and we'll continue next time.